The night sky hides immense chasms of nothingness, cosmic voids so vast they defy comprehension. These are not simply empty spaces, but the hidden architecture of the cosmos itself. This journey will fundamentally alter how you perceive the universe and your place within it. We will uncover how these colossal absences actively shape the cosmic web, the framework that binds every galaxy together. How did these voids form from the faintest whispers of the Big Bang? And what do they reveal about the dark energy tearing our universe apart? What do you believe is the true nature of the empty space between the stars? These voids are far more than just empty space. They are immense cosmic deserts, regions of such profound emptiness that if our own Milky Way galaxy were adrift in one, our night sky would be a near-total blackness, punctuated by only a handful of distant, lonely stars. This is the reality of a cosmic void. These are vast, underdense regions in the universe, typically spanning from 30 to over 300 million light-years across. Within these staggering volumes, the density of galaxies is hundreds of times lower than the cosmic average. They are the empty rooms in the cosmic mansion, the grand ballrooms where almost no one has gathered. Yet they are not perfect vacuums. Scattered within them are a few, very faint and isolated galaxies, like lone outposts in an endless wilderness, all held within a tenuous web of dark matter. The first hints of these colossal absences emerged in the 1970s and 80s, as astronomers began their first large-scale surveys of the heavens, meticulously mapping the positions of millions of galaxies. Instead of a random scatter, they found a pattern, a cosmic web of filaments and walls, and nestled between them, these immense and startlingly empty regions. The true significance of these voids lies in this very emptiness. They act as negative imprints of the universe's structure. By studying what is not there, by mapping the shape and size of nothing, we can infer the properties of the invisible dark matter scaffolding that defines everything we can see. It is a cosmic paradox where absence speaks louder than presence. This grand architecture transforms the cosmos from a star field into a living, breathing structure. Think of the universe as a colossal sponge, where galaxies cluster along the dense, interconnected walls and threads. These are the filaments of the cosmic web, vast rivers of dark matter and galaxies stretching across billions of light-years. Where these rivers intersect, they pool into immense galaxy clusters, the most massive gravitationally bound structures in existence. And between all these dense walls and nodes lie the voids, the enormous empty bubbles in the cosmic foam. This entire structure, from the densest knot to the emptiest void, is believed to have grown from the tiniest of seeds. In the first fleeting moments after the Big Bang, microscopic quantum fluctuations, smaller than a single atom, rippled through the fabric of space-time. Gravity then spent billions of years amplifying these tiny wrinkles. Slightly denser patches pulled in more matter, growing into filaments and clusters, while the less dense regions were left behind, expanding into the voids we observe today. The true backbone of this entire web is dark matter. This invisible substance, which does not emit or absorb light, forms a gravitational scaffold across the cosmos. Ordinary matter, the stuff of stars and planets, simply flows along this pre-existing dark matter skeleton, condensing where the gravity is strongest. This reveals a profound cosmic balance. The voids are not simply empty space left over after the universe formed its structures. They are an active, essential component of the cosmic web. Their immense, underdense volumes exert a kind of negative gravitational pressure, actively pushing the surrounding filaments and walls apart. The shape and distribution of these voids are a direct reflection of the underlying gravitational forces that sculpted them, a negative image of the universe's hidden mass. To truly understand how these great cosmic deserts reveal the framework binding all matter, we must first learn to see this invisible web. The work of a cosmic cartographer demands a special kind of patience. It is the patient mapping of billions of galaxies, one pinpoint of light at a time, across the unimaginable expanse of the observable universe. This monumental task relies on instruments like the Sloan Digital Sky Survey, a project that uses a dedicated telescope to methodically scan the heavens, capturing the light from millions upon millions of galaxies. For each galaxy, astronomers measure its redshift, the stretching of its light toward the red end of the spectrum caused by the expansion of the universe. This redshift acts as a cosmic ruler, allowing scientists to calculate the galaxy's distance from us. By plotting the precise three-dimensional positions of all these galaxies, a breathtaking map emerges, a chart of the cosmos that makes the grand design of filaments, walls, and the sprawling voids between them starkly visible for the first time. But observation is only one part of the story. To test our understanding of the physics that built this cosmic web, we turn to immense computer simulations. Projects like the Millennium Simulation take our known laws of gravity and particle physics and apply them to a virtual universe starting from conditions just after the Big Bang. Supercomputers then calculate the evolution of this digital cosmos over billions of years. The result is a simulated universe that we can compare directly to our real maps. When the simulated sky reveals the same web-like patterns and vast, empty voids as our telescopes observe, it gives us profound confidence that we are on the right track. A third, and perhaps the most ancient piece of evidence comes from the cosmic microwave background. This is the faint, relic heat from the Big Bang itself, a snapshot of the universe when it was just 380,000 years old. This afterglow is not perfectly uniform. It contains tiny variations in temperature, minuscule hot and cold spots that are the fossil imprints of those initial quantum fluctuations. These tiny ripples are the very seeds from which the entire cosmic web, with all its dense clusters and empty voids, would eventually grow. By combining these three powerful methods, direct observation of galaxies, sophisticated computer simulations, and the ancient light of the cosmic microwave background, we can trace the influence of the invisible components that govern our universe, dark matter and dark energy. So how does gravity, the force that pulls matter together, create such immense and expanding regions of nothing? Gravity's great cosmic work seems straightforward: to pull everything together. So how does it create such staggering emptiness? The answer lies in a cosmic imbalance, a subtle flaw in the fabric of the early universe. That story begins not with a dramatic collapse, but with a quiet deficit. In the first moments after the Big Bang, the universe was a searingly hot, nearly smooth soup of particles and energy, but it was not perfectly smooth. Thanks to those quantum whispers, some regions were ever so slightly denser than others, while some were just a fraction more sparse. Think of a vast, rising loaf of raisin bread. Most of the raisins are clustered close together, but a few areas have only one or two raisins, or even none at all. As the bread bakes and expands, those sparse regions do not just sit there. They grow far faster than the denser parts. The dough between the raisins stretches, and the empty areas balloon in size, becoming vast, airy caverns within the loaf. This is the genesis of a cosmic void. In our universe, gravity is the oven. Over billions of years, it acted with relentless patience on those tiny imperfections. The slightly denser patches had stronger gravity, so they pulled in more and more matter from their surroundings, eventually collapsing into galaxies and the great walls of the cosmic web. But what happened to the underdense regions, the places that started with just a little bit less? Their weaker gravitational pull could not hold onto their material. Matter began to slowly drain away, streaming out toward the hungry filaments and clusters next door. This outward flow created a runaway effect. As a void lost matter, its gravity grew even weaker, making it easier for still more matter to escape. The region became emptier and emptier, expanding faster than the universe itself. This is not a passive process. A mature void does not simply sit empty. It actively repels, while a massive galaxy cluster acts as a powerful gravitational attractor, pulling everything toward it. A vast void functions as a cosmological repeller, effectively pushing matter away. This happens because of the void's negative gravitational potential. Imagine you are at the bottom of a deep well, that is a cluster. Now imagine you are on a broad, flat hilltop that is steadily rising higher and growing wider, that is a void. Any matter placed on that expanding hilltop will naturally roll downhill, away from the center of the void and toward the denser regions at its edges. This gravitational push from emptiness is a dominant force, shaping the cosmic web on the largest scales. And this is where dark energy enters the story. As the universe ages, dark energy's influence grows, causing the overall expansion of space to accelerate. This acceleration acts like a tailwind for the voids, encouraging them to expand even faster and merge with their neighbors, creating the colossal 100 million light-year caverns we observe today. Sophisticated computer simulations show this evolution in breathtaking detail. We can watch as small, isolated bubbles of nothingness slowly stretch, become slightly elliptical, and then merge into giant, interconnected caverns, their boundaries defined by the flowing rivers of galaxies. The formation of a void is ultimately a story of cosmic subtraction, where having less allows a region to become profoundly more expansive and more influential. But if these regions are defined by their emptiness, what, if anything, remains inside these colossal cosmic caverns? A perfect void would be a chilling, absolute emptiness, but the universe rarely deals in absolutes. These cosmic deserts are not entirely barren. Drifting within them are a few isolated galaxies, the lone survivors of a great cosmic evacuation. These are the void galaxies, and their existence tells a story of profound isolation. Cut off from the bustling galactic cities of the filaments and clusters, they have evolved in near total solitude for billions of years. This isolation has preserved them in a kind of cosmic time capsule. Free from the gravitational harassment and cannibalistic mergers that constantly reshape galaxies in crowded environments, void galaxies are often smaller, richer in gas, and blazing with the blue light of newborn stars. They are like quiet, rural towns where life proceeds at a slower, more steady pace compared to the chaotic metropolis, but the galaxies are only the most visible residents. The space between them is filled with an incredibly thin, diffuse fog of hydrogen and helium gas, the primordial remnants of the Big Bang. This intergalactic medium is so sparse that it constitutes a better vacuum than any we can create in our most advanced laboratories on Earth. And yet, it is not nothing. Even here, in the deepest emptiness, the ghostly presence of dark matter persists, its gravitational pull faint but measurable, a diluted version of the scaffold that structures the entire cosmos. Perhaps the most subtle clue hidden within these voids is written in the oldest light in the universe. As the faint glow of the cosmic microwave background travels for billions of years across space, it passes through these vast, underdense regions. When a light wave climbs out of a deep gravitational well like a void, it loses a tiny amount of energy, causing its color to shift ever so slightly. This phenomenon, known as the integrated Sachs-Wolfe effect, is a direct imprint of the voids evolving gravity on the primordial light. It proves that these empty regions are not static holes, but active, dynamic players in the cosmos, their gravitational fields changing over time. The very nature of the galaxies and the gas within these voids, along with the subtle distortions they impose on ancient light, provides a unique record of the universe's initial conditions. These quiet, empty places are pristine laboratories, their simplicity offering a clearer view into the fundamental laws and the hidden components that govern everything. And it is the relationship between these voids and the universe's most dominant, yet invisible, forces that holds the key to our cosmic fate. The emptiness of a void is a perfect negative image of the universe's hidden skeleton. This is because dark matter, the invisible architect, dictates the entire gravitational landscape of the cosmos. Think of the universe as a vast, rolling terrain of hills and valleys. The dense clusters of galaxies are the deep gravitational valleys pulling everything toward them. The cosmic voids are the broad, expansive hilltops. Their gravitational pull is so weak that they effectively push matter away, sending it rolling downhill toward the denser regions. The precise shape and size of these empty hills are exquisitely sensitive to the fundamental nature of dark matter itself. For example, if dark matter were made of lighter, faster-moving particles, often called warm dark matter, it would have a smoothing effect. It would erase the tiniest wrinkles in the early universe, preventing the formation of smaller structures. The result would be a cosmic web with fewer but much larger voids. By contrast, the cold dark matter model, which posits slower, heavier particles, predicts a universe rich with a great many voids of varying sizes, exactly matching the intricate sponge-like structure we observe through our telescopes. This makes the voids themselves a powerful scientific instrument. By simply counting them, by measuring their diameters and mapping their intricate shapes, cosmologists can perform a fundamental test on the nature of the invisible substance that makes up most of the universe's mass. The most revealing details are often found at the edges. The boundary of a void is not a sharp wall but a steep slope where the density of dark matter increases rapidly. This boundary traces the invisible contours of the dark matter halos that surround galaxy clusters, like a topographical line on a map of an unseen mountain range. In this way, by meticulously studying the profound emptiness within these voids, we are actually charting the distribution of the invisible majority. This intricate dance between the seen and the unseen, between the glowing galaxies and the dark gravitational scaffold, points toward an even more mysterious and dominant force now shaping our cosmic destiny. The great cosmic voids are expanding, and they are doing so faster than the universe itself. This is the unmistakable fingerprint of dark energy, the most dominant and least understood force in the cosmos. Dark energy is the enigmatic pressure inherent to the fabric of space itself, a force that acts against gravity's relentless pull. While gravity works to clump matter together into galaxies and filaments, dark energy works to push everything apart, driving the accelerated expansion of the cosmos. This cosmic tug-of-war plays out everywhere, but its effects are most visible where gravity is at its weakest, deep within the emptiness of a void. In the crowded, dense regions of galaxy clusters, gravity is strong enough to hold its ground, keeping structures bound together even as space expands around them. But inside a vast void, gravity's feeble grasp is no match for dark energy's push. Here, the suppression of structure formation is almost total. Dark energy finds its greatest victory in these empty spaces, actively encouraging them to grow larger, faster, and to merge with their neighbors into ever more colossal caverns of nothingness. The very abundance of voids across cosmic time and the rate at which they expand becomes a powerful stopwatch for measuring the strength and nature of dark energy. Scientists can use the geometry of these voids for a remarkably clean test of cosmic expansion, known as the Alcock-Paczynski Test. The principle is elegantly simple. If we know what a spherical void should look like in a universe without dark energy, we can measure how it appears distorted in our own. The expansion history of the universe stretches the void along our line of sight, making it appear squashed or stretched. By measuring this apparent distortion, cosmologists can measure the expansion rate of the universe directly, independent of any other method. Another crucial clue comes from the motion of the few galaxies that linger at the edges of these voids. These galaxies are streaming outward, flowing away from the void's center and toward the denser filaments. This outflow velocity is a direct measure of the gravitational push of the void itself, a push that is either reinforced or counteracted by the background expansion driven by dark energy. By carefully observing how fast these galaxies are moving out of the emptiness, we can weigh the competing forces of gravity and dark energy with extraordinary precision. All of these observations, the growth, the shape, and the outflow from voids, are combined to measure the equation of state of dark energy. This single number describes the pressure that dark energy exerts, determining whether its strength is constant or changes over time. It is the key to predicting the ultimate fate of everything, and as if their growth and the motion around them were not enough, the very shape of these voids tells another, equally profound part of the story. The geometry of a void is never a perfect sphere. If you could somehow hold one of these cosmic caverns in your hand, you would find it slightly squashed, a subtly distorted bubble. This shape, this morphology of nothing, is not random. It is a detailed historical record, a frozen snapshot of the forces that have pulled and stretched at the fabric of space for billions of years. The very ellipticity of a void reveals the gravitational tides exerted by the massive filaments and clusters that surround it. Picture a soft clay ball held between your fingers. As you squeeze, its shape deforms, becoming elongated. On a cosmic scale, the dense walls of the cosmic web act like those fingers, sculpting the empty regions between them. This is why small, young voids often appear relatively round, isolated bubbles in the primordial foam. But as the universe ages, these voids expand and inevitably collide with their neighbors. They merge, their walls break down, and they stretch into vast, interconnected, and often highly irregular tunnels of emptiness. This tendency for voids to become more elongated and filamentary as they grow is a key prediction of our standard model of cosmology, one built upon the foundation of cold, dark matter. The shape of the void, therefore, becomes a direct test for the invisible architecture of the cosmos. Some alternative theories of physics, those that seek to explain the motions of galaxies without invoking dark matter, propose modifications to Einstein's theory of gravity itself. These modified gravity theories often make a very different prediction about the shapes of these empty regions. In such a universe, voids would tend to be more spherical, less distorted by the surrounding structures. By carefully measuring the ellipticity of thousands of voids, astronomers can perform a clean, decisive experiment. Do the voids match the predictions of a cold, dark matter universe, or do they point toward a new law of gravity? The answer, written in the subtle squash and stretch of these empty spaces, consistently reinforces the presence of the dark matter scaffold. The internal structure of a void is just as telling as its external shape. The emptiness is not uniform. Typically, the center of a void is a broad, shallow basin of incredibly low density. Then, as you move outward toward the edges, the density profile steepens dramatically, like a cliff face rising from a calm sea. This sharp boundary marks the transition from the void's repelling core to the attracting influence of the surrounding cosmic web. This specific density profile acts as another constraint for our computer models of structure formation, telling us exactly how matter drained away over cosmic time. To make sense of this vast population of empty regions, cosmologists employ advanced statistical tools with names like the void probability function. This isn't as intimidating as it sounds. It is essentially a way of quantifying the emptiness, of asking questions like, how likely are we to find a void of a certain size in a given volume of space, and how are these voids themselves clustered together? The answers provide a precise census of nothingness. This meticulous mapping of the geometry of emptiness transforms voids into one of cosmology's most powerful tools, a standard ruler. We know from the physics of their formation what size and shape a typical void should have at a given point in the universe's history. When we look out into the distant universe at voids billions of light years away, we can measure how they appear to our telescopes. If the ruler appears distorted, if the voids look squashed or stretched compared to our expectations, that distortion is a direct measure of the universe's expansion history across those vast cosmic epochs. We are using the shape of nothing to chart the growth of everything. This very geometry of emptiness provides one of our most precise cosmic measuring tapes. In cosmology, a standard ruler is an object whose true physical size we know with confidence. When we look out into the universe and measure how big that same object appears to be across the sky, that apparent size tells us its distance, and that distance, in turn, reveals how much the fabric of space has stretched during the light's long journey to us. For decades, astronomers have used the remnants of sound waves from the infant universe as such a ruler. These are the Baryon acoustic oscillations, or BAO. In the first 400,000 years after the Big Bang, the universe was a seething plasma, with ordinary matter and light locked in a tight embrace. Gravity tried to pull matter into clumps, while the intense pressure of the light radiation pushed it back out. This created powerful sound waves, spherical pressure waves that rippled outward through the primordial soup. Then the universe cooled just enough for atoms to form, releasing the light in a great flash and freezing these waves in place. The result was a cosmic preference, a specific scale imprinted on the distribution of matter. This scale, about 500 million light-years across, became a fundamental unit for the cosmic web. And it is this very same scale that dictates the characteristic size of the cosmic voids we see today. The walls of the cosmic web tend to form at a certain separation, which means the empty bubbles between them naturally settle into a typical diameter, around 100 million light-years. This gives us a known, calibrated ruler. We know what size these voids should be. Now, imagine looking deeper and deeper into space, which also means looking further back in time. By surveying the universe at different redshifts, we can measure the average apparent size of voids from different cosmic epochs. If the universe were not expanding, those distant voids would look the same size as nearby ones. But if the expansion of space has stretched the distances, then a void of a known physical size will appear larger or smaller on the sky depending on the era we observe. It is like having a collection of identical coins but seeing them from different distances. The farther away the coin, the smaller it appears. By carefully measuring how the apparent size of our standard void changes across cosmic history, we can reconstruct the entire expansion history of the universe. This method is exceptionally powerful because voids are such clean environments. Unlike dense galaxy clusters, where chaotic mergers and complex astrophysics can obscure the underlying signal, the quiet, simple emptiness of a void preserves the pristine imprint of the early universe. The clustering of the voids themselves, the pattern of how these empty regions are spaced apart from one another, also carries the clear, strong signal of those ancient Baryon acoustic oscillations. Using voids as standard rulers offers a complementary and often more precise measurement of dark energy's properties than methods relying solely on galaxies. It turns the grandest absences in the cosmos into exquisitely calibrated instruments for fundamental physics, and the information they carry stretches back even further to the very first moments of everything. The subtle squash and stretch of these cosmic caverns is a direct echo from the very dawn of time. The grand architecture of the cosmic web, with all its filaments and voids, was not a random occurrence. Its blueprint was drawn in the first unimaginably fleeting moments of the universe, during a period known as inflation. In less than a blink of an eye, the cosmos underwent a violent, exponential growth spurt, inflating from a subatomic speck to a volume larger than our entire observable universe. This rapid expansion did something crucial. It took the faintest quantum whispers, the microscopic fluctuations inherent to spacetime itself, and stretched them across the cosmos. These minute ripples in density became the seeds for all structure, the cosmic DNA that would eventually dictate where galaxies would blossom and where these immense voids would form. We can still see the imprint of these seeds today, frozen in the faint temperature variations of the cosmic microwave background. That ancient light map is the universe's baby picture, showing the slightly denser hotspots and less dense cold spots that gravity would spend billions of years sculpting. The cold spots, those regions of slightly lower density, are the direct progenitors of the great voids we observe. This means the statistical properties of the void population are a direct reflection of those initial conditions. How many large voids exist compared to small ones, and how these empty regions themselves cluster together in space, directly mirrors the statistical character of the primordial fluctuations. Cosmologists describe this with a parameter called the spectral index, which essentially measures the balance between large-scale and small-scale power in the early universe. If the primordial fluctuations had more power on vast scales, the result would be a universe dominated by fewer but far more colossal voids. By meticulously counting and measuring these empty regions, we are effectively reading the original recipe for the cosmos. This makes voids one of our most powerful tools for testing theories of the very early universe. Certain exotic models of inflation, or even alternative scenarios like a bouncing cosmos, predict a distinct fingerprint in the void population, a specific pattern in their sizes and distribution that would stand out clearly against the predictions of our standard models. Studying these great cosmic absences is a form of archaeology, allowing us to probe physics at energy scales 1 trillion times greater than anything the Large Hadron Collider can ever achieve. They are our clearest windows back to the first fraction of a second, to the very laws that set existence into motion. In their profound emptiness, they hold the encoded story of creation itself, a story we are only just beginning to decipher. Einstein's theory of gravity has been tested for over a century, from the bending of starlight to the timing of distant pulsars, and it has never failed. Yet the cosmic voids present a new and profound challenge. Their immense emptiness offers a unique stage to question whether our understanding of gravity itself is complete. The persistent mysteries of dark matter and dark energy have led some physicists to propose radical alternatives, theories where gravity behaves differently on the vast scales of the cosmos. One prominent idea is modified Newtonian dynamics, or MUND, and its more complex relativistic cousins, In these frameworks, there is no mysterious dark matter. Instead, the strange motions of galaxies and the very structure of the cosmic web are explained by a subtle change in the laws of gravity, a new force that emerges in regions of extremely weak acceleration. Where better to test this than in the deepest voids, places where gravity's pull is at its absolute faintest? These cosmic deserts become pristine laboratories, far removed from the messy astrophysics of stars and supernova that complicate studies of dense galaxy clusters. In a universe governed by Einstein's general relativity with dark matter, a void expands at a predictable rate, its gravitational field shaped by the unseen dark matter scaffold. But in some modified gravity theories, a void should grow faster, its emptiness accelerating outward in a way that general relativity alone cannot explain. Its internal density profile, the way the void's emptiness deepens toward its center, would also have a distinct signature. How can we measure this? Astronomers turn to two powerful techniques. They watch the motions of the few isolated galaxies at the void's edge, tracking their outward flow to see if it matches Einstein's predictions or hints at something new. Even more revealing is the phenomenon of weak gravitational lensing. As light from incredibly distant galaxies travels billions of years to reach us, it passes through these voids. While a void contains very little mass, the surrounding filaments of dark matter exert a gravitational pull. This warps space-time, bending the light from the background galaxies and distorting their shapes in a subtle, coherent pattern. By mapping this faint distortion, we can essentially weigh the invisible mass distribution around the void. A deviation from the expected lensing signal would be a direct hit against the standard model, evidence that gravity itself works differently in the grand emptiness. So far, the data from vast surveys like the Dark Energy Survey strongly favor the cold dark matter model. The voids we see behave just as Einstein's theory, bolstered by dark matter, predicts they should. But the search is far from over. Each new, deeper map of the cosmos pushes these tests further, probing the frontiers of our knowledge. The very existence of these great nothings forces us to confront the role of chance in our cosmic understanding. What if the universe we can see is just one particular arrangement, one where general relativity happens to hold sway, and the true, fundamental laws of nature are waiting to be discovered in the next great void, or the one after that? Our entire view of the cosmos is framed by a single, unchangeable window. We have only one observable universe to study, a fact that introduces a fundamental uncertainty known as cosmic variance. This is the statistical noise that arises because we can only observe one specific outcome of a random process. The universe we see might not be perfectly average. It could simply be one particular roll of the cosmic dice. This uncertainty becomes most profound when we study the very largest structures like the grandest cosmic voids. For these colossal absences, cosmic variance is immense. We cannot know for sure if the biggest void we have ever found is truly representative, or if it is a rare statistical fluke. A perfect example of this puzzle is the KBC void, a potential underdensity hundreds of millions of light years across that might contain our own Milky Way galaxy. Is our home nestled inside a truly exceptional cosmic desert, a rare bubble of emptiness in an otherwise average cosmos? Or is this void entirely ordinary, a structure well within the expected distribution of the standard model? The answer hinges entirely on understanding the probability of such a thing existing. To distinguish a bizarre anomaly from a simple statistical outlier, cosmologists must first calculate the expected range of void sizes and densities. This is where massive computer simulations become absolutely essential. By generating thousands of mock universes, each with a slightly different random seed, scientists can create a cosmic census of what is normal. They can ask, in how many of these simulated universes does a void as large as the KBC void appear? If such a void appears in only 1 out of every 10,000 simulations, then our place in space might be genuinely peculiar, potentially pointing toward new physics or a flaw in our models. But if a void of that scale shows up frequently, then it is simply part of the expected cosmic tapestry. This inherent statistical uncertainty forces a humbling realization. Cosmology is not always about certainties, it is often a science of probabilities. The largest structures we catalog might not be fundamental features of the cosmos, but rather the equivalent of a lucky streak in a grand cosmic lottery. This statistical lens, forced upon us by the sheer scale of these great nothings, connects directly to one of the most profound implications of their existence. These growing voids are not merely features of the cosmos, they are its destiny. The ultimate fate of everything we see is being dictated by the accelerating expansion of these vast, empty regions. We live in the era of dark energy, a time when this mysterious pressure dominates the cosmos, and its effects are most starkly visible in the profound emptiness where gravity's voice is just a whisper. As dark energy relentlessly pushes, the cosmic web itself begins to fray. The delicate filaments, those great rivers of galaxies, will be stretched to their breaking point. Galaxies will be pulled from these threads, drawn into the dense clusters at the intersections, which will become the last bustling cities in an ever more desolate cosmos. These clusters will transform into isolated islands, adrift in a sea of nothingness that grows colder and darker with each passing moment. This is the trajectory we are already on, a future of cosmic isolation written into the expansion of every void. But there exists an even more extreme possibility, a final, violent end known as the Big Rip. In this scenario, dark energy is not constant. Its repulsive strength grows fiercer over time. First, it would tear apart the cosmic web, then it would rip galaxies from their clusters. Later, it would pull stars from their galaxies. In the final, horrifying moments, it would overcome the very forces that hold atoms together, tearing apart every molecule, every atomic nucleus, and finally, the fabric of spacetime itself. While this is a speculative and far future possibility, it illustrates the ultimate power that dark energy could wield, a power we first observe in the gentle, yet relentless, growth of the voids around us. Long before any such cataclysm, a profound isolation will set in. As the expansion accelerates, driven by the voids themselves, a cosmological horizon will shrink around us. Distant galaxies will be carried away by the stretching space faster than their light can travel to us. One by one, they will wink out of the observable universe, their light eternally lost. Our entire view of the cosmos will collapse down to a single, lonely collection of galaxies, our local group, bound together by gravity in a final, tight embrace, while an impenetrable blackness closes in from all sides. Voids are the harbingers of this cold, bleak future. Their accelerating growth is the most direct observable we have of a universe sliding toward the heat death, a state of maximum entropy where all structure has faded into a thin, uniform, and lifeless haze. To study a void today is to hold a preview of the universe's final chapters in your hands. This grand narrative, from the quantum seeds of creation to the cold silence of the end, forces us to confront our place in a cosmos whose ultimate story is one of dissolution, written in the ever-expanding language of nothing. This profound emptiness forces a radical shift in how we see ourselves. For centuries, humanity placed itself at the center of creation, but cosmic voids reveal a stunning truth. Over 90% of the volume of our universe is composed of these vast, empty regions. We, living on a tiny, vibrant planet, are the true cosmic anomaly. The voids are not the exception, they are the default. The background state of the cosmos is a cold, dark, and near-perfect vacuum. The galaxies, the stars, and life itself are the rare and fleeting interruptions in this overwhelming silence. This inverts our entire perspective. Fullness and structure are the cosmic luxuries, not emptiness. This realization echoes ancient philosophical traditions, particularly in Eastern thought, which long contemplated the fundamental role of non-being. Emptiness is not a void in the negative sense, but a fertile ground from which all things emerge and to which they return. It is the silent canvas that gives the painting its meaning. In the cosmos, existence is defined as much by what is absent as by what is present. The great walls of galaxies have meaning only because of the profound voids that separate them. Scientifically, this teaches us a powerful lesson. To understand the whole, we must study the wholes. By mapping these absences, we are not just tracing a physical scaffold of dark matter and galaxies. We are uncovering a conceptual framework for our own place in the cosmos. We are not at the center of anything. We are transient inhabitants of a small, dense node in an immense web, a web that is itself being pulled apart by the growing nothingness that surrounds it. This is a humbling, yet strangely liberating, gift from modern cosmology. It situates our entire story within a grander, more impersonal narrative. To move from this philosophical vantage point to practical discovery, we must ask how we can possibly measure and quantify such profound nothingness. Finding these immense cosmic deserts requires a special kind of cartography. How do you map a hole in a universe filled with data points? You cannot simply point a telescope at an empty patch of sky and declare it a void. The process is a delicate computational dance, sifting through the positions of millions of galaxies to identify the significant absences between them. This is the work of advanced void-finding algorithms. One powerful method is known as Zobov, which stands for Z1s bordering on voidness. This technique treats every galaxy in a survey as a point and constructs a unique cellular structure around it called a Voronoi tessellation. Imagine pouring water onto a surface covered with pebbles. The water will flow into the spaces between the pebbles, forming a network of interlocking pools. Each pool is a Voronoi cell, and its size is inversely related to the local density of galaxies. A huge cell means there are very few galactic neighbors. The algorithm then identifies vast, contiguous regions of these large, empty cells and classifies them as a cosmic void. Another approach, the watershed void finder, uses a different analogy. It treats the three-dimensional map of the universe as a topographic landscape. The dense galaxy clusters are the high mountain peaks, the filaments are the ridges, and the voids are the vast, deep drainage basins. The algorithm simulates pouring water over this cosmic terrain, watching where it flows and collects, with the voids being the catchment areas where all density flows away. But these digital tools face significant challenges. A galaxy survey is not a perfect, boundless snapshot of the cosmos. It has edges and boundaries, and some areas are observed more deeply than others. The algorithms must carefully account for these selection effects to avoid mistaking an unobserved region for a true void. An even trickier problem comes from redshift space distortions. When we measure a galaxy's distance by its redshift, we are actually measuring the sum of two motions, the overall expansion of the universe and the galaxy's own peculiar velocity as it falls toward a dense filament or away from a void. This can make the void's boundary appear smeared or distorted, like a reflection in a rippling pond. The algorithms must untangle these motions to find the true underlying emptiness. Defining the void itself is surprisingly difficult. Where exactly is its center? How do you mark its fuzzy, transitioning edge? Is it best described by its effective radius, assuming a perfect sphere, or by its more complex elliptical shape? These definitions are not just academic. The precise way a void is delineated can directly influence the cosmological parameters, like the strength of dark energy that we derive from it. This is why the development of these tools is such an active frontier. Researchers are now turning to machine learning, training artificial intelligence on vast simulated universes to recognize and classify voids more efficiently and robustly than any rigid set of rules ever could. The very act of defining nothing has become a sophisticated science, proving that even emptiness requires the most careful quantification. And with these refined catalogues of nothingness in hand, we can ask the most profound questions about the forces that shaped them, tracing their lineage back to the universe's first violent moments. These giants of emptiness stretch the very definition of a void. Among the catalogued chasms, the Boötes void stands as a legendary example, a cavern of near-nothingness so vast it could comfortably contain tens of thousands of galaxies like our own Milky Way. Yet within its staggering 330 million light-year breadth, astronomers have found only a few dozen. If our solar system were located at its center, we would not have known other galaxies existed until the 1960s. This is an emptiness of almost inconceivable scale, but even the Boötes void is dwarfed by a candidate known as the giant void in Canes Venatici, a potential abyss spanning over 1 billion light-years. To cross such a distance at the speed of light would take longer than the current age of Earth. The existence of these supervoids presents a direct challenge to our standard model of cosmology. According to the cold dark matter framework, structures should form with a certain expected range of sizes. These behemoths exist at the very tail end of that probability distribution. Are they simply rare statistical flukes, cosmic lottery winners in a universe governed by known rules? Or does their immense scale hint at something more exotic? Perhaps a feature in the primordial power spectrum from inflation that gave these specific regions an extra push toward emptiness from the very beginning. Their influence is not merely theoretical. We can detect their gravitational footprint on the oldest light in the universe. As photons from the cosmic microwave background travel for billions of years, they must climb out of the deep gravitational wells of these supervoids. This arduous journey saps their energy, causing a minute but measurable drop in temperature, a cold spot imprinted on the cosmic microwave background map. This is the integrated Sachs-Wolfe effect in action, a direct link between the largest structures of nothing and the first light of creation. Studying these grand canyons of the cosmos provides the most stringent stress tests for our models. They are the extreme environments that reveal the limits of our theories, forcing us to ask if our universe is merely one probable outcome or if it contains anomalies pointing toward new physics. To complete our understanding, we must also turn our gaze to the opposite end of the scale, to the smallest and most numerous of these empty spaces. While the giant voids capture our imagination with their staggering scale, the true texture of cosmic emptiness is far more intricate. Emptiness comes in all sizes, forming a vast hierarchy that stretches from billion light-year chasms down to miniature voids nestled within the walls of the cosmic web itself. These are the mini-voids or subvoids, underdense regions spanning a mere few million light-years. You can find them in the great galactic filaments, the dense walls of galaxies, and even floating like bubbles within the emptiness of a larger parent void. This creates a nested structure of nothingness, a fractal-like pattern of absence that mirrors the intricate filigree of the cosmic web as a whole. This multi-scale architecture was precisely seeded by the initial conditions of the universe. The nearly scale invariant fluctuations from inflation, meant that tiny density deficits were imprinted on every conceivable scale, from the supercluster level down to the realm of individual galaxy groups. As gravity did its work, it amplified these deficits in parallel, creating a full spectrum of void sizes. The largest underdensities ballooned into the Boötes like giants, while the smallest ripples grew into these local mini-voids. Their existence is a direct prediction of our standard cosmological model, and finding them in exactly the abundance and distribution we expect is a powerful confirmation of our entire cosmic origin story. But these mini-voids are more than just cosmic curiosities. They are active participants in the life of galaxies. A galaxy residing in a local mini-void, even one within a larger dense filament, experiences a profoundly different environment than its crowded cousins. With fewer galactic neighbors, it faces less gravitational harassment and fewer disruptive encounters. More importantly, the low-density environment directly impacts its fuel supply. The thin gas that permeates a mini-void can flow onto the galaxy more smoothly, potentially leading to steady, sustained star formation. This provides a crucial link between the vast field of cosmology and the detailed astrophysics of individual galaxies, showing how the large-scale cosmic landscape directly influences the birth of stars on the smallest scales. This hierarchical view of emptiness transforms voids from simple curiosities into a precision toolkit. By analyzing the full spectrum of void sizes, cosmologists gain multiple, independent ways to measure the universe's fundamental parameters. A giant void and a mini-void will respond differently to the expansion history and the nature of dark energy. Using voids of all sizes as standard rulers offers a powerful cross-check, reducing the statistical uncertainties that plague measurements from a single scale. This multi-scale approach is not a luxury, but a necessity as we stand on the brink of a new era of discovery, the next generation of telescopes like the Variance, Rubin Observatory and the James Webb Space Telescope will map the cosmos with unprecedented depth and resolution, revealing millions more voids down to the smallest scales imaginable. In their silent, layered emptiness, we will find the clearest echoes of the universe's first moment and the most precise map of its final fate. The silent cartography of emptiness is about to be transformed by a new generation of cosmic observatories. These instruments are not simply bigger telescopes, they are fundamentally new eyes on the universe, designed to map the voidscape with a precision we have only dreamed of. The Vera C. Rubin Observatory's legacy survey of space and time will scan the southern sky for a decade, cataloging an estimated 20 billion galaxies. This will produce the most comprehensive three-dimensional map of the cosmos ever created, revealing the fine, filamentary structure of the cosmic web and the subtle shapes of millions of voids with stunning clarity. In space, the Euclid mission and the Nancy Grace Roman Space Telescope will take this precision even further. They are designed to perform exquisitely sensitive weak lensing measurements. By observing how the light from billions of background galaxies is warped as it passes the dark matter halos surrounding voids, these missions will, for the first time, allow us to weigh the invisible scaffolding of the entire cosmic web directly. They will see the gravitational hills and valleys sculpted by emptiness itself. Meanwhile, the square-kilometer array, a colossal radio telescope network, will map the universe in an entirely different light. Instead of looking at galaxies, it will detect the faint emission from neutral hydrogen gas that permeates the cosmos. This will trace the cosmic web in its most primordial form, revealing how voids have drained not just galaxies, but the very gas from which they are born. The sheer volume of data from these projects will be transformative. discovering millions of voids rather than just thousands will finally overcome the problem of cosmic variance. We will no longer have to wonder if the voids we see are rare flukes. We will have a true statistical census of nothingness, a complete picture of the universe's empty architecture. This will turn voids into a high-precision laboratory. By comparing the shapes, sizes, and growth rates of these millions of voids against the predictions of Einstein's theory, we can perform the most stringent test yet of general relativity on the largest scales. Any subtle deviation, any hint that gravity behaves differently within these vast emptinesses would point toward revolutionary new physics. The nature of dark energy will be pinned down with unprecedented accuracy. Is its strength truly constant, or does it evolve over time? The answer is written in the accelerating expansion of these voids, and the next generation of maps will read that story with perfect clarity. To interpret this coming flood of data, we must also build universes inside our computers. The fidelity of our cosmological simulations must leap forward to match the quality of our observations. These digital twins will incorporate not just dark matter and gravity, but the complex physics of gas, magnetic fields, and the formation of stars and black holes. Only by creating a perfect simulated void can we understand every nuance of a real one. We are standing at the threshold of a golden age for the science of emptiness, where the grandest absences in the cosmos will become our most precise instruments for decoding the fundamental laws of reality. These digital universes are born from pure mathematics, a cosmos rendered in lines of code. Projects like Illustris TNG and Uchu start with the same initial conditions we believe sparked our own universe, a hot, dense state imprinted with quantum fluctuations. Then, supercomputers take over, calculating the gravitational dance of billions, even trillions, of dark matter particles across billions of years. But these are not sterile simulations of invisible matter alone. The most advanced models, like Illustris TNG, weave in the messy, beautiful complexity of baryonic physics. They simulate the cooling of gas, the violent birth of stars within that gas, and the explosive feedback from supernova and supermassive black holes that can heat the surrounding material and blow it far out into space. This intricate feedback is crucial because it directly impacts the environment within a void. A powerful galactic wind can push remaining gas out of an underdense region, making it even emptier, or it can trigger star formation in a lonely galaxy, changing its very nature. Inside these virtual cosmos, we can run the same void-finding algorithms used on real telescope data. We can pinpoint a specific void, track its growth from a tiny underdensity into a vast cavern, and dissect its properties with perfect knowledge. We know exactly how much dark matter it contains, the precise strength of its gravitational push, and the complete history of every galaxy that ever drifted within its borders. This controlled environment transforms voids into a scientific playground. We can ask profound what-if questions by simply changing the initial rules of the simulation. What if dark matter particles were lighter and faster, a scenario known as warm dark matter? We run the simulation and watch as the cosmic web simplifies, with smaller filaments wiped away and the voids becoming noticeably larger and fewer in number. What if Einstein's theory of gravity needs modification on cosmic scales? We input the new equations and observe how the shapes of the voids change, perhaps becoming more spherical or expanding at a different rate. By comparing these alternate reality voids to the vast catalogs from real surveys, we can rigorously test these ideas, validating our standard model or finding tantalizing discrepancies that point toward revolutionary new physics. These virtual laboratories are the essential training ground for the coming data deluge. They help us refine our algorithms and understand the subtle biases in our observations, ensuring we can extract every drop of meaning from the billions of new galaxies we are about to map. One of their most exciting revelations lies in the unique, isolated galaxies that call these cosmic deserts home. Deep within the cosmic desert, a lone galaxy spins in tranquil isolation. These void galaxies are not just celestial hermits, they are pristine laboratories offering a glimpse into galaxy evolution in its most undisturbed state. While galaxies in crowded clusters are constantly jostled, merged, and stripped of their gas by violent interactions, a void galaxy evolves in profound serenity. This peaceful existence leaves a distinct signature. Unperturbed by galactic neighbors, these systems can hold onto their vast reservoirs of primordial hydrogen gas for billions of years longer. This abundant, cool gas fuels a more extended and steady pace of star formation, unlike the frantic, bursty star birth triggered by collisions in denser regions. The result is often a smaller, bluer galaxy, glowing with the light of many young stars. They are also chemically simpler, with lower metallicities, meaning they contain fewer heavy elements forged in previous generations of stars. This makes them remarkable cosmic relics, resembling galaxies from a much earlier epoch in the universe's history. Their simplicity is their greatest scientific gift. By studying void galaxies, astronomers can cleanly separate the internal drivers of galactic life, like the slow and steady cooling of gas to form stars, from the external, environmental drivers that dominate in busier parts of the cosmos, such as galactic mergers or the brutal ram pressure stripping that occurs when a galaxy plows through the hot gas in a cluster. Projects like the Galaxy and Mass Assembly Survey, or GRMA, have been meticulously designed to seek out and analyze these faint, isolated systems. Their very existence and specific properties, their mass, their gas content, their star formation rate, provide a crucial test for our most sophisticated models of galaxy formation. Any successful simulation of the universe must be able to explain not only the giant ellipticals in dense clusters, but also these small, gas-rich spirals and irregulars adrift in the great nothing. They complete the picture of galactic ecology, yet the journey of their light through the immense emptiness adds another layer to their story, a subtle effect that transforms them into beacons illuminating the void itself. Even the most precise cosmic map is subtly warped by motion. When we chart the universe using Redshift, we are not just measuring the serene expansion of space, we are also capturing the frantic, peculiar velocities of individual galaxies as they rush through the cosmos. This creates a telltale distortion in our three-dimensional charts. Galaxy clusters appear flattened, squeezed together along our line of sight, while the vast cosmic voids appear stretched into elongated, finger-like shapes pointing directly back at us. These are not mapping errors. These redshift space distortions are a goldmine of dynamic information, a direct imprint of gravity in action. The pattern is most clear around a void. Galaxies at its edge are not sitting still. They are flowing outward in a coherent river of motion, draining away from the center of emptiness and toward the denser filaments. This grand exodus leaves a specific fingerprint on our redshift maps, stretching the void's apparent shape. By meticulously measuring this stretching, cosmologists can calculate the speed of this outflow. This velocity is not random. It is dictated by the total gravitational pull of all the mass, both visible and dark, surrounding the void. This allows us to measure a crucial number known as F sigma 8, which quantifies the rate at which cosmic structure is growing. It tells us how fast the cosmic web is tightening, and the voids are expanding at this moment in cosmic history. This single measurement becomes a powerful test for the laws of gravity themselves. Einstein's theory of general relativity combined with dark matter makes a very specific prediction for how quickly structures should grow over billions of years. Alternative theories, like those that modify gravity, predict a different rate. The outflow from voids provides a clean, large-scale experiment to see which prediction matches reality. To extract this delicate signal from the noisy cosmic map, scientists use sophisticated statistical tools like the void-galaxy cross-correlation function. This technique carefully compares the positions of galaxies to the centers of thousands of voids, revealing the subtle but consistent pattern of their outward motion. The dynamic fingerprint we find in the distorted shapes of nothingness offers one of our purest measures of the gravitational forces sculpting the cosmos, connecting the grand motion of galaxies to the fundamental nature of spacetime. Einstein's equations gave us a beautifully simple model of the cosmos, a universe that is smooth and uniform on the grandest scales. This ideal, described by the Friedmann-Lemaitre-Robertson-Walker metric, assumes the cosmos is the same in every direction, a perfect cosmic fluid. Yet our maps reveal a reality far more textured, a universe carved into great walls and immense empty voids. These voids are not minor imperfections. They are the most prominent departures from cosmic smoothness, and their existence forces a profound question. Does the lumpiness of the real universe, with its fast-expanding voids and slow-collapsing clusters, change the very fabric of spacetime itself? This idea is known as backreaction. Imagine the universe as an ocean. The standard model treats it as a calm, flat sea, with a steady tide rising from a mysterious source, dark energy. The backreaction hypothesis suggests a different picture. What if the ocean's surface is actually a churning chaos of deep troughs and powerful jets? The average rise of the sea level might not be from a single tide, but from the combined effect of all these swirling motions. In cosmic terms, the rapid expansion within vast voids and the sluggish contraction within dense clusters could combine to create the illusion of an overall accelerated expansion. It is a radical proposition that dark energy might not be a new, mysterious force, but an emergent property of the universe's own intricate structure. Current evidence suggests this backreaction effect is likely too small to explain the full force of dark energy we observe, yet it remains a vibrant and crucial area of research, a testament to how these great emptinesses challenge our most fundamental assumptions. Even if they are not the sole driver of cosmic acceleration, their geometry provides one of our cleanest windows into the universe's true shape. The Alcock-Paczynski Test uses voids as exquisitely calibrated cosmic spheres. We know what a spherical void should look like based on the physics of its formation. When we observe one in the distant universe, its apparent shape is distorted by the expansion history along our line of sight. If the void appears squashed, it tells us one story about how space has stretched. If it appears stretched, it tells another. This distortion is a direct measure of the universe's expansion rate across billions of years, a measurement independent of any other method. Voids, therefore, exist in a profound dual role. They are structures within spacetime, but their collective properties also help define the spacetime they inhabit. The very geometry of these empty regions, their sizes and their distribution, is a reflection of the universe's global curvature and the nature of the dark energy that fills it. This deep connection between the local, the texture of the cosmic web, and the global, the overall fate of the cosmos, is a thrilling frontier. It means that by mapping the grandest absences, we are not just charting the distribution of galaxies. We are reading the subtle warping of the cosmic stage upon which everything plays out. And as with any frontier, this one is not without its own debates and open questions, reminding us that our map of the cosmos is still being drawn. Even our most powerful tools for mapping nothingness are not without their limits. the very definition of a void remains surprisingly fluid, a source of ongoing debate among cosmologists. Different algorithms, each with its own mathematical philosophy for identifying emptiness, can scan the same galaxy survey and produce noticeably different catalogs of voids. One method might identify a vast single cavern, while another breaks that same region into several smaller, interconnected bubbles. This is not a simple error, but a fundamental uncertainty in how we delineate absence. The consequence is a systematic wobble in the cosmological parameters we derive. The measured strength of dark energy, for instance, can shift depending on which catalog of nothing you choose to believe. Compounding this is the challenge of galaxy bias. The galaxies we can see are merely tracers, a sparse population of lights in a sea of invisible dark matter. In the dense urban centers of galaxy clusters, this tracing is relatively faithful, but in the desolate voids, the relationship breaks down. The few isolated galaxies that do persist may not be honest representatives of the underlying dark matter distribution. They could be late-arriving stragglers or unusually resilient holdouts, giving us a skewed impression of the void's true gravitational landscape. This means the emptiest places in the cosmos are also the hardest to read with confidence. The grandest voids themselves are at the center of a heated statistical debate. Structures like the Boötes void stretch the limits of what our standard model of cosmology predicts. Are these billion light-year chasms once in a universe flukes, rare but permissible within the laws of probability? Or are their immense sizes a whisper of something missing from our models, a hint of exotic physics in the primordial universe that gave these voids an extra push toward emptiness? The evidence is similarly puzzling when we look at the cosmic microwave background. Those telltale cold spots, which should be imprinted by the gravitational pull of supervoids, often appear fainter than our theories predict. The universe's oldest light seems less affected by these great absences than we expected, creating a tension between the world of galaxies and the whisper of the Big Bang. Modeling the life of a void is itself a formidable task. The equations describing their growth and dynamics rely on approximations that work well for average regions, but they can break down at the extremes within the most vast and rapidly expanding emptiness. These are not failures of the science, but the very signs of a living, breathing field of research. Each limitation is a precise question, and each controversy is a rigorous debate that drives the entire discipline forward. This honest acknowledgement of uncertainty leads us to one of the most captivating controversies of all, a question about our own place in the cosmic tapestry. Our own cosmic address might be far emptier than we ever suspected. A controversial but compelling idea suggests our Milky Way, along with the entire local group of galaxies, is drifting inside a vast underdensity known as the local hole or the KBC void. This proposed region spans an astonishing hundreds of millions of light-years, a bubble of relative emptiness where the density of galaxies is noticeably lower than the cosmic average. If this model is correct, then we are not in a typical part of the universe. We are residents of a grand cosmic desert. This is not just a curiosity of our location. It is a potential key to unlocking one of the greatest mysteries in modern cosmology, the Hubble tension. This is the persistent and puzzling disagreement between two ways of measuring how fast the universe is expanding. Measurements based on the local universe, using stars and supernova as mileposts, consistently give a faster expansion rate than measurements based on the early universe, derived from the cosmic microwave background. The discrepancy is small but significant, implying a fundamental flaw in our understanding or our measurements. How could living in a void create such a discrepancy? Think of it like being in a region where the ground is already sinking. if you measure how quickly objects are moving away from you in this local sinking zone, you might get an inflated sense of how fast the entire landscape is subsiding. In cosmic terms, the weaker gravity inside a vast void means matter here is not as tightly bound to the cosmic whole. The space within the void expands a bit faster than the global average, tugged less by the collective gravity of the surrounding dense web. So, the Hubble constant we measure from our local, under-dense perspective would be artificially high, potentially explaining a part of that troubling tension. The implications are staggering. It would mean a fundamental parameter of cosmology, the Hubble constant, carries a local bias based on our cosmic address. The debate, however, is fierce. Is the KBC void a real physical structure, or is it simply a statistical fluke, a lucky coincidence that we happen to be in a slightly emptier patch of an otherwise average cosmos? This is the hard limit of cosmic variance, the idea that with only one universe to observe, we can never be entirely sure what is normal. Careful reanalysis of galaxy surveys is ongoing, with some studies finding evidence for the underdensity and others arguing it falls within expected statistical noise. The question cuts to the heart of cosmology itself. Are we special or are we average? For centuries we thought we were central, then we learned we were not. Now, we must confront the possibility that our home resides in one of the universe's grand, quiet rooms, and that this very emptiness is subtly distorting our view of the entire cosmos. These silent, expanding caverns complete our cosmic portrait. They are the essential negative space that gives the entire cosmic web its meaning and form. Every property of a void, from its vast diameter to its subtle elliptical shape, acts as a data point in a grand cosmic experiment. Their sizes tell us about dark matter. Their distribution reveals the pattern of primordial seeds. Their accelerating growth measures the relentless push of dark energy, and their gravitational influence tests the very laws of physics on the largest scales imaginable. Voids are not merely empty, they are dynamic, evolving entities that serve as our most pristine laboratories. They are standard rulers for measuring the universe's expansion, particle physics experiments for probing the nature of dark matter, and fundamental tests for theories of gravity. By meticulously studying this cosmic nothing, we illuminate the everything. We use absence to understand presence. This holistic view reveals the true cosmic mass budget, accounting for the invisible dark matter scaffold and the mysterious dark energy that fills the void itself. The universe is a unified system, a cosmic dance where emptiness and structure are equal partners, forever locked in a push and pull governed by gravity and expansion. This is the ultimate goal of cosmology, to see the universe not as a collection of isolated objects, but as a single, interconnected framework, and the transformative power of this pursuit lies in a profound realization. By choosing to study nothing, we have ultimately discovered everything. These cosmic voids teach us a profound and humbling lesson. The grand framework of the universe is not built from starlight alone, but is equally defined by the immense, silent spaces in between. We have traced the invisible skeleton of dark matter by mapping these empty regions, felt the push of dark energy in their accelerating growth, and tested the very laws of gravity within their quiet borders. Their very existence is an echo of the quantum whispers from the dawn of time. The ultimate insight is this: to truly comprehend the cosmos, we must give the voids as much weight as the galaxies. The hidden architecture that binds every particle of matter is sculpted as much by these colossal absences as by the glittering nodes of light. We live on a pale blue dot, a fleeting spark of life adrift in a cosmic arena whose true form is a delicate balance between presence and absence. So the next time you gaze into the night sky, do not see only the stars. Let your eyes adjust to the darkness between them and contemplate the vast, informative nothing that gives the light its context and its meaning. We would love to hear how this hidden framework has shifted your perspective. Share your thoughts in the comments and subscribe for more journeys to the heart of space's greatest mystery.